Hi, everybody. Can you hear me okay? I think you can. It's nice to see so many of you. Okay, today's talk is over-the-air updates in the wild, lessons from the field. Let me first shortly introduce myself. I'm Jana. I come from Serbia, and I have majored in electronics and hardware, but found my passion in embedded Linux, and that's where I chose to pursue my career. At the moment, I work for Northern Tech, which is a company based in Oslo, and that is the company that has developed Mender, the over-the-air open source update solution. This will not be a talk about Mender at all. I just wanted to mention it, and I will mention it a few times over the course of the talk, but the topic of this talk is in general OTAs. Okay, so what are we going to cover here? First, I will walk you through what over-the-air updates are and why do they matter. I will try to explain what makes OTA hard. Afterwards, we'll talk about different update modules and architectures and tools that are available on the market at the moment. I will finish my presentation with best practices and takeaways, and hopefully we'll have some time for questions in the end. Okay, if I wanted you to remember one thing from this talk, it would be that I would want to try to explain to you how important OTAs are in the industry and how overlooked that topic often is. Okay, before I begin, I'd like to get to know you guys. Can you tell me, are all of you engineers? Yes, okay, good. How many of you work in embedded? Most of you, great. Then how many of you have worked with OTAs before? Good amount of you. Okay, I am surprised. And how many of you have worked with Mender? Okay, that's good. Like I said, it will not be Mender-based topic. I just wanted to know. Okay, why over-the-air updates matter? And why it is still your concern what happens to the product after it leaves the factory? So what are over-the-air updates really? OTAs are a method of remotely delivering and installing software updates to connected devices, such as IoT devices, vehicles, smartphones, etc., any smart devices, without the need for physical interaction. Physical connection can still happen. You can have your devices connected over Ethernet, but what's important is that there is no need for you to physically interact with the device, that you can update it remotely. To which devices does this apply to? It applies to all embedded Linux devices, such as gateways, sensors, etc. IoT devices, which may or may not be running Linux, they can be running real-time operating systems. And in the end, essentially, it applies to every device with internet connectivity. By update, what do I mean by that? We can update full system images. You can update the full kernel, full operating system, or you can choose to update only individual apps or services, or maybe something even smaller, such as config files or security keys. So what's here at stake? First of all, we have security. Nowadays, hackers are very well aware that embedded devices very often are not updated at all, and they take advantage of that. So what happens when you discover a vulnerability on your device after it has been shipped into the field? It's very important for you to have a way of delivering a remote update quickly so the hackers cannot take advantage of that. Of course, bug fixes. I've never seen a product shipped into the field without a bug. I don't know if any of you have. And for these reasons, once again, it's very important to be able to ship the fix after the device has already been deployed. It allows you to resolve crashes, regressions, or some logic errors. When it comes to feature updates, once again, it's very important for your device to be competitive and relevant on the market by being able to add some new capabilities, protocol, UI features, etc. Sometimes you ship a product when you're very well aware some new features will be needed, but sometimes your customers come back wanting some new features. And instead of having to ship back your product or develop a new version of it, it's just easier to update it remotely. And lastly, but probably the most important, is cost savings. When you have OTA implemented, you can avoid expensive on-site service calls, meaning you do not have to send a technician for every issue that appears. Additionally, shipping costs will be lower and downtime will be minimal. It's very expensive to update manually thousands of devices, but if you have OTA implemented, it should be as simple as a single button click. Okay, so what are the risks of not having OTAs? First of all, we have brick devices, something that happens more than you'd think. It can happen for many reasons. One failed upgrade, or one wrong bug fix, or internet service which just went down and never came back up. And for that reason, once again, instead of sending some guy to fix it in the field, it's just easier to be able to access it remotely. Of course, after that, we have security exposure, which you want to keep to a minimum. And when you don't have OTAs, it automatically increases your support load, which all leads to brand damage and lost opportunities for your business. So, section 2. It sounds simple, what I just explained, like updating your devices remotely. So in reality, why is it so complex? Let's talk about it. I have tried to sum up some of the key principles that every OTA solution on the market must follow. First of all, we have interruption resilient. What happens if you have tried to update your device, but it's interrupted? It can happen for many reasons. For example, it lost network, it lost power. Whatever the reason is, the device must be able to recover from that state. It can never get stuck in a state which is in between the update state. It must be able to come back to the previous working version. It also must be retry safe. If one update fails, what happens? How does the device come back and retry again? Those are some of the things that you need to think about in advance. Third principle is that the updates must be atomic. And what does that mean? It means that the update must be installed on your device fully or not at all. And there cannot be an in-between state. So either update is successful and fully working, or the device rolls back to the previous version. It can never get stuck. And lastly, of course, we have security. And all of the updates should be cryptographically signed and verified. And all of the secrets should be protected during and after the update has finished. So let's talk about the first challenge, which is unreliable network, which is something that's probably most common in the field, because with embedded devices, they are almost never online for the full amount of time. Very often those devices come online occasionally, once a day, once a week, or even once a month. Some of these devices have challenging network configuration. They can be behind NATs, firewall, captive portals, or unmetered or intermittent LTEs. So what can go wrong in this case? Partial downloads, timeout edge cases, or for example, device having multiple updates lined up because it has not checked in with the server for a long time. And then how does device choose which update to install? If it has version 3 waiting, but also there are version 5 and version 6 which came in during that time, does the device jump straight to the latest version, or does it install versions one after the other? That's also one of the considerations that you need to make. So in this case, what do you need to do? You need to enable resumable downloads and retries. There need to be connectivity checks both before and after the update, and you must implement handling for all various connectivity scenarios. Okay. The next two challenges are storage constraints and signing and security. As you are aware, when it comes to storage, embedded devices usually have very, very limited memory. Sometimes it's just one flash chip with a few hundred megabytes. Sometimes it's even less. And how does OTA complicate it? Well, it complicates it because with OTA you need to have enough space for the current system, of course, but you also need to save space for the new update payload, which will be installed. You need to store it somewhere before installing it. And also you need to have a rollback image or a recovery partition. I will speak more about rollback and recovery partitions in the following slides. In this case, if your storage is limited, what can help is compression, streaming, or having maybe delta updates, but still your storage is something that you should be very well aware of. What happens with each of the megabytes on the device, you should know. When it comes to signing and security, I believe it's self-explanatory. All of the updates must be signed, verified, and authenticated, especially in the nowadays when everything is so easily hackable. You also need a way to protect all of the secrets and credentials of the device and firmware integrity during and after installation. Moving on, we have safe rollback and atomicity, observability, and feedback. Okay, so what really is rollback? Atomicity I have already explained, but when it comes to rollback, it's exactly when the update is being installed, and if anything goes wrong, rollback means that the device will be able to roll back to the previous working version. Without rollback, a failed update can break your device. Atomicity, I have mentioned what it is, and solutions like A/B partitioning or having a recovery partition are what helps when it comes to rollback. A/B partitioning, I will explain in the following slides, but if you're familiar with Mender, you're probably aware already what it means. When it comes to observability and feedback, I feel that that is often overlooked, especially by software engineers, because in embedded devices, that's something that you need to pay close attention to. You need to be aware if your update has succeeded, of course, but you also should be able to get the logs even if the update is successful, because you need to know how is it behaving when everything goes right. That will help you debug it when something goes wrong. So you need to know whether the device has even attempted a new update, did it boot into the new version, or did it roll back silently? Because when it comes to updates, it's something that happens silently. Your customers should not be aware of the update going on. It should be boring, not flashy at all, but still you need a way of staying aware of what is going on with all of your devices. Okay, versioning and compatibility. What if a device missed 3 updates and now tries to jump ahead? Is it safe to apply, for example, version 5 over version 2? Also, you need to think about how do you manage dependency changes, application data migrations, or rollback logic. When it comes to testing, this is something that's greatly more complicated when it comes to embedded devices, because you're not just testing software, you're testing storage limits, bootloaders, rollback logic, power cycles, so many things which cannot be tested with a simple unit test. Okay, so to summarize the challenges that I have mentioned here, I'd like to point out once again to unreliable connectivity, limited storage, security, which is non-negotiable, rollback and failure recovery, and testing, because it's not simply about delivering the update, it's that it needs to be done safely. Otherwise, you're even in a worse position than you were before you started with OTAs. Okay, section 3, I will talk about different update modules and architectures. There are many different ways of doing OTAs. I don't want to say that any is better than the other, because it's not. They are all very different and can be applicable to various different devices. It just depends on what kind of system do you have and what your needs are. So some of the considerations that you need to take before making a decision what OTA is right for you is storage, safety, recovery needs, and update frequency. Of course, there are many more considerations, but these feel like the most important ones to me. Okay, so let's look at the most common patterns and trade-offs. AB dual root file system is something that I mentioned when I talked about rollback. So, how does ABA work? Basically, on your device, you would have, for example, 4 partitions. It does not have to be, it can be more of them. But when you have AB, you need to have 2 root file systems. One is A, one is B. One will be active, the other one will be inactive at that moment. The last 2 partitions are, for example, for the bootloader, and they can be, the 4th one can be for persistent data, which stays persistent across all of the updates. So, why is there a need for 2 root file system? First of all, like I said, your operating system will be running from partition A. Let's imagine that. When a new update comes in, device polls the server, checks whether there is an update, and if there is, device downloads the update to the partition A, where the OS is running from, and begins silently installing the update to partition B. While this is going on, your device is still operational. There's no downtime. You can still use it normally. At some point, okay, I think the internet was the issue. Okay. At some point, the installation on the new partition will finish, and you can still use your device normally. But when you decide you want to switch to the new system, you will reboot your device. Bootloader will change passive and active partitions, and on the next boot, it will boot from partition B. But what if something goes wrong? What if you're not satisfied with the update? In that case, device can roll back to the partition A, where your old system was. How do you know something went wrong? For example, you can add some manual checks, custom checks, as a service or as a script which runs once after boot, and if all of those checks passed, you can choose to commit to the update, or if it has not passed, you roll back to the previous versions. Sometimes the system will not boot at all. In that case, bootloader will just simply choose the old partition. Okay, so that's the basic principle of AB partitioning, but very often you will not have enough space for this. So what do you do then? How do you keep your device secure? Sorry, I forgot I have also this slide before going to recovery partitions. Okay, so the question is, why even bother with AB? Because it's complicated, it takes a lot of space. First of all, because of safe rollback, because of atomic updates, because of minimal downtime, because you are able to use your device while the update is being installed, which is something that Windows users will never know what it looks like. And also, it's real-world proven. Today, there are many different operating systems and devices using it, and it's proven to be very, very stable and safe approach. But if you don't have AB, what are your options? The recovery partition. In this case, you have only one root file system, and the updates are applied to this system directly. But you also have a separate small recovery partition, which will contain a minimal operating system image. So if something goes wrong and the device becomes unbootable, bootloader can always fall back to the recovery image, and it gives the system some time to install the last known good image or request help from a remote server. This approach does impose downtime for the device, especially if something goes wrong mid-update. But like I said, you can have more available space for some of your other needs. So this is really one of the trade-offs that you need to make. What's more important to you, whether it's not having a downtime or saving memory? Okay, let's talk about types of updates. We have application level updates or system level updates. Application level updates would be updating only a part of the system, which usually happens in user space. These updates can be containers, for example, Docker, or files simply dropped into a directory, or least often it can be packages being updated. Most of the times, these updates are applied without the need to reboot the system. And in this case, you do not need a special partitioning scheme. No need for a recovery partition or AB if you are only updating applications in user space, and there's no risk of compromising the operating system itself. On the other hand, second approach is what I've been talking about all along, which is system-level updates, where you are updating a whole OS image or just a kernel, where you basically replace the entire root file system or some of the major components. And as mentioned, it usually involves rootfs AB swaps or a recovery partition. And in this case, it's always necessary to reboot into the new system. Next, let's discuss delta or full images. The easiest approach will always be installing a full image onto your device, because you don't want to have a risk of comparing the images, etc. So it's easiest always to install the full image. That's unfortunate. Okay. I hope the sound is still okay. If you do not want to install a full image, or if you simply do not have memory for that, there is a solution which is called delta updates. In this case, the payload will contain only the differences between your current image and the new image being installed, and only that difference will be applied. In this case, you're saving a lot of memory. It can be as small as 10% of the original image. But one trade-off that's very common is that these delta updates usually require having a read-only file system. So once again, a trade-off. What's more important to you, having a read-only, having more memory, or installing the full image? Okay, let's talk about different ways to trigger the update. We have automatic, manual, or phased rollouts. Manual updates. These are the updates which you trigger on your own manually by pressing a button on the server. This is very common in development and staging because it gives you the most control and the best overview of the system. And it's very common in safety-critical systems, which require a human oversight. What are the cons of this approach? It doesn't scale. It's not very good if you have thousands of devices. And it's very error-prone because humans bring in errors. What are the pros of this approach? Maximum control. And also, it's great for diagnostics and troubleshooting. Second approach is automatic updates, which are probably the most common. In this scenario, devices occasionally check in with the server whether there is update available, and they can install the update, apply them on their own. These updates can be time-based. For example, device checks in with the server every 6 hours or so, or once a week, depends on the device, or they can be triggered by an event which triggers the device to check for the update. And this is very common in consumer devices, smart devices, and also in unattended field devices. What are the cons of this approach? It's risky if update breaks something, which of course OTA should be able to help you with if done properly, and it also requires robust rollback and validation. Pros of this approach are that it is hands-on, it's scalable. It does not matter whether you start an update for 5 devices or 5,000, and it ensures that your whole fleet stays up to date. Okay, phase rollout. I'd say that this approach is less common, but still very, very useful. So what does it really mean? In reality, if you have thousands of devices, you might find it risky to update them all at once. Because what if something goes wrong and then you end up with all of the devices having a wrongly installed operating system or the worst case scenario being bricked? So what you may want to do is start small. You may want to, for example, do the update first for 5% of the devices. And then if everything goes okay, if the devices report back to the server successfully, you may update 20% more of the devices. And then lastly, what's left is 75% of devices which you can do in a bulk after you have confirmed that first two phases went smoothly. Why does it matter? Like I said, it prevents you from breaking all of the devices at once, and it gives you time to catch regressions or edge case failures. Okay, in section 4, let's talk about tooling landscape, or what are the tools which are available on the market at the moment. So, there is many of them. These are not all. These are the ones that I have myself seen most often, although I am not an expert on all of them. Some of them I have not even tried yet, so don't ask me questions about those ones. And also there's one thing that I want to mention, which is not on this slide, but it's also very common. It's having your own custom solution that you grew in-house in your company. I think that it's very, very popular nowadays for your company to develop a custom OTA solution and have designated developers working on it, but I also think that many companies nowadays are switching to the solution which is available on the market because of maintaining it. At some point, OTA just becomes too complex and too difficult to maintain, and it makes sense to switch to a solution which has proven to work in the industry. Okay, so let's start with Mender. What's special about Mender is that it provides both server and the client components, meaning on the device you will have a client component installed. But Mender also provides a server where you can store all of your artifacts and you can control the updates from the server. The server can be hosted in your own infrastructure, or you can choose the Mender hosted, which is available. But it can be open source, where both the client and server are open source. Source code can be found online, but you can choose to pay for it if you want some of the enterprise features. Okay, so on what systems does Mender work? It works on all embedded Linux devices. Some are easier to integrate, some are harder, but that's just the reality of embedded devices. And since recently, it also supports Zephyr, and there is plan in the future for it to also work on free RTOS. Like I mentioned, server can be hosted or self-hosted, and it supports multiple update types: full images, containers, or custom updates. When it comes to bootloaders, at the moment it supports U-boot, grub, or some custom solution, depends on the board. Okay, moving on to SW update. This is a device-only solution, which is probably the one major difference. If you want to have a server, you can very, very easily integrate Hawkbit into it. I will talk about Hawkbit next. It provides modular framework. It's very, very, very customizable, which makes it both great and terrible at the same time. Because if you want to have an update solution specifically tailored to your needs, SW Update is a great solution. But also, if you want something that's just easy and works out of the box, then I would say it's not so great solution, because it requires a very steep learning curve and a lot of time to get into it and understand the approach that lies behind the SW Update. It requires manual integration with the bootloader. It does not work out of the box, and when it comes to bootloader, it supports U-boot grub and FE boot guard. When it comes to partitioning, I don't know if I mentioned, for Mender, it supports AB updates only, while SW Update supports both AB and approach with having a recovery partition. Okay, so what is Hawkbit, which I mentioned on the previous slide? Hawkbit is basically OTA management server. It provides you with a web UI and APIs, but it does not provide a client which would be running on the device. It's meant to be integrated with update solutions like SW Update, Rauk, or some customly developed in-house solutions. What's important to note is that it is not actively maintained anymore, but it's still very, very widely used in the industry. Okay, next we have RAUC, which I have not tried personally, but from what I know, it's a bundle-based approach. It has great Yocto integration, which is very important. But for it to work, the bootloader must support boot slot handling. This approach is also very simple and lightweight, but it has no built-in orchestration. And it also has a Hawkbit compatible backend. Okay, moving on, we have Balena, which is a container-based OTA platform. So it does not do full system image upgrades, and it works on a defined platform which was developed by Balena and which is Yocto-based. This approach is designed for fast deployment of application changes. Okay, so I have told you about only some of the solutions available on the market, but how do you know which one is good fit for your device? There are, once again, many things to take into considerations and many trades-offs that you need to make. So, storage. Once again, storage is very important. How much storage do you have? Do you need rollback support or not? Will you be updating full system images or not? What kind of licensing do you need when it comes to open source? Is customer support an important factor? Like, do you need somebody who's available to help you with your updates 24/7 or not? Most importantly, how much money are you willing to spend on this? And do you need full device management for the full fleet or just OTA? And lastly, how much customizations do you want to make to the update flow? I have asked ChatGPT to summarize these solutions, and I think it did a pretty good job. I will not go through this in detail because most of this I have already discussed, but I will leave it on the slides in case anybody wants to circle back to it later. Okay. I'm coming to my section 5, which is best practices and takeaways. I'm really good with my time, so there will be plenty of time for questions or for a coffee break. But I also think there is lunch coming up after this session. Yeah, I need it too. Okay, so like I said at the beginning of my talk, the most important thing I want you to take from this talk is how important OTAs are in the industry and how overlooked they are. And while it's something that can be very complex to integrate, on the other hand, it should be something that's very easy to use. So you need to find the perfect balance. So when it comes to key takeaways and best practices, I want to say that most importantly, roll back early. You should not be confident in yourself, in your devices, that failures will not happen, because they will. Sooner or later, you will experience what it means for the update to fail. So you need to plan for rollback early in your deployment cycle. Second, version everything. It doesn't matter whether it's images, configs, keys. You should treat everything as source code, because if you do not have a proper versioning system, you have no way of reproducing your builds. And if something goes wrong with the build, with the image in field, you have no way of testing it in your laboratory. Thirdly, monitor updates. You need to track both successful and failed updates to be able to know what is going on with your devices in field and track any anomalies that might happen. Fourth, make updates boring. Like I said, updates should not be something flashy, spectacular, no balloons when it happens. It should be something so boring that the customers have no idea it went on. One day they come to work, device is working fine. Overnight it updates on its own, and tomorrow it's still working fine. Customer should not know anything was going on with it. That's why your updates should be predictable. Low drama releases are the goal. Remember, OTA is a journey. So start simple. Start with application updates, and then over time grow to full system images. Or start with manual updates, and over time grow to automated or phased rollouts. If you start with all of the features available as soon as you want to implement OTAs, I think that's a recipe for a disaster. So for that reason, start simple, and over time it will grow, it will become more stable. But for this, you need to plan early. And lastly, I want to say that trust is the products, because firmware updates carry the user confidence. If user experience devices which are bricked, which are stuck in an unknown stage, which have a significant downtime, they will lose trust in your product. Okay. And lastly, this brings me to question and answers. Are there any? Yeah, go on.
You touched a little bit on that. By the way, very nice that you managed the noise.
I hope you were able to hear me.
Well, I was.
Okay.
You managed that heroically, so well done. But I was interested in testing sort of strategies, maybe tools, testing on OTA updates. You touched on that, but
yeah, I have only touched on that because that's not something I have implemented myself, to be honest. If somebody didn't hear, the question was about testing of the embedded devices. And I do not have a direct answer for this because...
testing the OTA update process.
Oh, the OTA update process?
Or testing updates on devices.
Yeah, only updates, not the whole like embedded system. That's something that's most of the times needs to be developed and customized to the update flow. Like, for example, adding systemd services to your device and the bash scripts, which would, on the first boot, test whether everything is correct, is a good way of reporting and giving like detailed logs for you to know what is going on. But you also need a way which is faster and which can, for example, automatically compare those logs, whether they were successful or not. But as far as I'm aware, at the moment, there isn't a solution on the market which does this for you. Because every device and every update is so greatly different from the others. And I feel that this is something that very often customers don't take into consideration, thinking, it will not happen, why do you need this? Why do I need to develop it on our own? So my answer is basically that as far as I'm concerned, there isn't an out-of-the-box solution for this, but it is something that needs to be developed by your own company. Okay, any other questions? Yeah?
Wondering if you have any recommendations for Delta update library.
Delta update library.
Like if you have your own solution and you need Delta updates.
But you're using OTA, which was developed in-house?
Yes.
In that case, I do not have a recommendation. Yeah, I've never done Delta updates which were standalone. Only with an update manager, which is already available on the market. So I can provide guidance on that. Sorry. Okay. Yeah.
You said that Delta updates usually require a read-only file system. Can you expand on that?
Yes, of course. So the question was about Delta updates and why do they require a read-only partition? Because what Delta updates basically does is, like I said, you want to install just a simple payload on your device which contains only the differences between the current system and the one that's being shipped from the server. But how do you make that comparison? The file system needs to be read-only in order for you to do that, in order for you to compare the new system to the old one. Because if something is being written to the old file system, or if there are many changes, there is no way for you to make a new payload which will only contain the comparison. I have not seen Delta updates which worked without a read-only file system, but I do not want to say that they don't exist. Prove me wrong. But so far, this is the most common approach that I've seen. Okay.
And on this question, will it be possible to have just on read-only the parts that is the target for the Delta and the rest would be written right?
Theoretically, yes. In practice, that's something that you would need to customize on your own, depending on, of course, which OTA you are using. But I think that is absolutely doable because you do not need to upgrade the whole operating system at once. it can be separated in different bundles. It all depends on how do you want to approach it. And I don't see any issues with a certain part of it being just a read-only and making delta off of that, while the rest of it can be writable, or having just a simple writable partition while the biggest chunk of it is a read-only. That makes more sense. So yeah, that approach can be done, and I think it's very good because in this case you still have a certain partition where you can write changes, temporary folders, etc., which increases the complexity of integration, but also reduces the complexity of your usage because you're able to write to it. Yeah?
Do you know of any solutions on the market that would be suitable for devices that are in air-gapped networks? Because when I've been working with Vendor before, we had the devices check in with the server.
Mm-hmm.
But if you have embedded devices that never are online per se,
Mm-hmm.
maybe only talk with one central entity, how do you do the device management? How do you like?
Am I still allowed to say Mender? Because Mender does have another approach without using the server. There is something called a gateway, where you have one device which occasionally checks with the server. That device should be connected to the rest of your fleet, which can be offline constantly. And that gateway will download the payload, the image, from the server and distribute it locally to the rest of your devices. But still, the problem with that approach is that you need one device which is online or checks in periodically. Or in your case, do you have that? Is there any devices which goes online?
Maybe.
Okay, obviously not. Yeah. In that case, first thing that comes to mind is storage being difficult, because without Wi-Fi, without internet, you're relying on which protocol for communication?
We were just talking hypothetically now.
Okay, in theory.
Like if we want to like embark on this journey, how should we do it?
Okay, so internet is not a must-have, but you need to be able to have some protocol which can, whether it's Bluetooth, for example, or LoRa or whatever, which can send the payload to your device. But if you are working with protocols like LoRa or Zigbee, they need to be much smaller than they normally would over internet. But it's absolutely doable. And you would, once again, need to have only one gateway, which can the payload be sent to, and that gateway can distribute it to the rest of the fleet. But yeah, I'd say that is a very common approach in embedded systems. Having internet will always be like the easiest approach, but definitely there are ways of doing it without the internet connection. Any other questions? Okay, thank you for coming.